This is the 19th lesson on universal gravitation. We're going to go ahead and learn a few things. We're going to learn about what universal really means when it comes to gravity. We're going to know the variables of the universal gravity equation. We're going to be able to solve for any of these variables that you see right in here. And we're going to determine how one variable, if one changes, how it would change other variables in the equation as well. So first of all, Isaac Newton had a big idea. He saw the moon just going straight across the sky. Apples are falling from the sky. And he's just wondering, why is one doing one thing and the other thing's doing another? So he started thinking a little bit bigger, a bigger picture, once again his big idea, and he realized, you know what, the moon really isn't just going straight across the sky. The moon is actually coming back every day over and over and over, and is actually following a curved path around the Earth. So something else must be happening. And so he realized that the moon's inertia keeps it going forward, but at the same time it's falling. And so the result of that is it's following a curved path going around the Earth. So the moon itself is acting like a projectile being thrown around the Earth. And the combined action keeps it in this orbital path that we have. What was Isaac Newton's big idea related to gravity? Well, the big idea he has is that all objects are going to attract all other objects. And we'll see that a little bit more in a bit. Why does the moon not collide with the Earth if there's an attraction? Well, the moon's going forward and falling. So this going forward and falling creates instead of straight forward or instead of straight down, creates this orbital path around the Earth. Newton's law of universal gravitation, we're going to take a look at any object with a mass. So this is his big idea right here. Every object attracts every object. All objects, you attract your pencil, you attract your neighbor, you attract the ceiling, you attract the Earth, you attract everything around you, no matter if you can feel it. There is a force between you and your coffee cup in the morning. The amount of force depends on the distance, and it's related by this really, really small number. So that's why you don't feel the attraction from anything except for the Earth. The Earth you feel because it's such a massive planet. But something small as a pencil you're not going to feel. So these are the different variables. There's the equation we're going to use. Fg equals g m1 m2 over d squared. That's force of gravity equals the universal gravitation constant. Once again, in this weird unit, you don't have to really think about the unit too much. You're using the number, not the unit much. Times the mass of one object, times the mass of a second object, divided by the distance, but this is going to be squared. So it's going to be important. Sometimes you have to watch a question. If Joe is on the Earth, this distance might be between him and the center of the Earth, or the radius. So there could be other ways that it might be stated where it is the distance, but it sounds like something else. So the force is going to be in newtons, just like before. Masses are going to be in kilograms. We're going to have distance in meters. Universal gravitation constant, once again, it just goes to knock everything out. So everything that you plug in goes back and becomes a Newton at the end. And then the acceleration due to gravity, just because we're going to talk about it, it is not. Just look at it. If it was g, if little g was g, it would be the same unit. This is an acceleration. This is something else. Universal gravitational constant, this is going to be the same constant for all objects that are next to other objects. It's not to 10 meters per second squared. It's not that, so be aware of that. It's not that little g. It's something different. It's on your equation sheet. You'll see g, capital G equals 6.67 times 10 to the negative 11th. It's a really small number. If I go ahead and make it a small number and show you, this negative 11 means at that point you're going to go 11 times. It's going to be a really tiny number. You need a really, really big, massive number to actually feel the force of gravity. So let's say a 70 kilogram person is not going to feel attraction to a 70 kilogram person because this g is just way too small for you to feel the effects. Gravity, universal gravity is the weakest fundamental force. There's four other forces we'll talk about later on: electromagnetism, the weak interaction, strong interaction within the nucleus. We'll deal with all that later on, but for now, just know this is really weak, and actually the weakest, to just be aware of that. We're going to look at rule of ones of universal gravitation. There's a way we can deal with problems when we see something like this and we see that a number has something is doubled, but we don't really see, you don't see kilograms, we don't see meters. We've got to do a little bit more with it. So we're going to go ahead, and this is just a rule ones. I call it the rule ones. I don't know if everybody calls it the rule ones, but we're going to find the equivalent. We're going to take that equation, the most related to what's going on here. We're talking about distance and we're talking about force of gravity. So we have distances, force of gravity. That's good enough. We have something we can relate to something else using an equation. We go ahead and we rearrange it, and actually it's already rearranged for FG, and we determine the equivalent. So FG, the equivalent of FG is saying the same thing as G M1 M2 over D squared. And we're going to take that equivalent and we're going to put it over itself. And we're developing a ratio of befores to now. And anything before it should be multiplied by 1 because 1 times itself was itself. But anything new that wasn't changed would still be 1 times itself. Then they said nothing about M1 or M2. And when we're doing the rule of ones, G will always be 1. G is not going to change from that value from before. It's always going to be 1, not 6.67 times 10 to the negative 11th, unless you're using kilograms and newtons and different things like that. And then, so we put it, the only thing that changed here is we have to double the distance. So we go ahead and we find that distance, we double it. We still have to keep that squared there. And so 1/4 times would be the answer here. Okay, what happens to the force of gravity when you double the mass of both objects? We go to the same equation. Everything down the bottom gets 1. We double the mass of 1 and mass of 2. It doesn't matter which one's which. And we multiply those together, and we get 4 times the original. What happens to force of gravity when you double the mass of one object and double the distance between the objects? So we're going to go ahead and once again, everything down the bottom is going to have 1s. Once you realize this is going to be a 1, you don't even have to worry about it in your calculations. We're just doing the top part. So we double the mass of one object. So that's what that says right there. Double the mass of one object, and we double the distance. We double the distance, still keeping that squared, and we get 2 over 4, which is now 1 times. And you'll see when you get in the practice set later on, you just if you had an original number like 1,000, you just multiply 1/2 times 1,000, and the new value would have been 500 newtons if that was the case. So you just multiply by this. That's what the times just means. You multiply by the original value if you knew it, and if you don't know it, this is the answer, 1/2 times. Okay, so this is the universal gravitation force, how force relates to mass. If mass goes up, force goes up equivalently. And you can see that by the line, which number 5 asks you, question 5, draw the shape of the graph. It should look something like that. As force increases, as mass increases, force is going to increase as a result. The mass of one object increases. What happens to the force of gravity and what rate? It's going to increase at a constant rate, and it's seen by the straight line, the straight line that's sloped. So it's increasing because it's sloped up, but it's constant because it's a straight line. How is universal gravity compared to the force compared to distance? Well, it's not just underneath, so it's not just inverse, but it's also inverse. We call it inverse squared. It's inversely proportional to the square of the distance. So a little bit of distance change actually has a big effect, and it has a diminishing effect as you go on and on and on and on and on. So it has a greatest effect at the beginning, and so you should have on your paper, you show some sort of curve. I didn't throw numbers in here, so you don't have to have any sort of scale, but just some sort of curve like what you see I drew here. And this is showing you that diminished rate. It's going down because it's sloped down, but it's less and less sloped down as you keep on going. It's becoming flatter. Rearranging the equation, you should be able to rearrange the equation. So if I want to rearrange this equation for M1, what I'm going to do is I want to keep M1's on top, so I just want to get rid of everything else. I'm going to multiply D squared out from both sides. That's going to get rid of that part. I'm going to divide out the G and the M2. I'm going to divide out the G and the M2. And so when that's all done, G's cancel out, the M2's cancel out. I'm left off with M1 equals, just rearrange FG times D squared over G times M2. Another thing to be aware of, make sure you have extra parentheses around the denominator. You want to make sure these are together. A lot of calculator issues happen when someone doesn't have an extra parentheses. And if you just write it like this and you multiply G times M2, what the calculator is going to do is it's going to throw it up top. It's going to do something you don't want it to do. So make sure when you're typing in numbers, extra parentheses, making sure this is in the denominator kept together. Okay, so the next thing you need to be able to solve for is the D squared. The thing you see here with D squared is you actually have to get rid of D squared first. You need to get it to the top. It can't be on the bottom. Because if you got rid of everything right here, you would be left off with a 1, which is still 1 over D squared. It's not D squared. And we don't even want D. We're going to do another step to get rid of the D squared, the squared part of it. We're going to have to multiply both sides by D squared. When you multiply both sides by D squared, this is really the same as saying FG over 1. So we multiply both sides by D squared, it gets rid of the d squared here and it puts it up top. So it's no longer in the denominator. But now we don't want this FG, so we're going to divide out the FG from both sides. Divide out the FG from both sides. And lastly, we don't want the squared, so we're going to take the square root of both sides. And this is what you get. Make sure everything's in the parentheses. So you have to take the square root of everything in there. Okay, so let's go ahead and do some practice problems. This one, there's a lot of big numbers. So I just want to show you, when you're typing in something like 6.67 times 10 to the negative 11th, 6.67 times 10 to the negative 11th. Well, when I type this in, I'm going to go ahead and I'm going to type in 6.67, and I'm going to hit, at that point in time, I'm going to go to, I want to find this button right here where it says EE. In order to do that, I'm going to do second and I'm going to do shift. When I do second and shift, it's going to show me this value. It's going to show this E in my calculator. And at that point in time, I'm just going to go ahead. The next thing I'm going to type is negative 11, and I'm going to see exactly that number in my calculator. I'm not going to see it times 10 too. I'm not going to see anything else. But if I'm trying to take this number in my calculator, it's going to look like that number. What this is going to do is it's going to keeps that negative 11 as a times 10 to the negative 11 attached to 6.67. It helps the calculator organize the numbers a little bit better, and you be more aware of what you're doing. You need a little fewer parentheses, but I would still include the parentheses whenever possible. So if we're typing in this number, so the Earth is 6.6, or so we have our G. Once again, we're not doing log ones. We're not doing 1 times something. So we're going to have a real G. We're going to have that number, universal gravitation constant off of your equation sheet. Here's Earth. I already rounded it a little bit more than some answers you'll have, or questions you have a little bit later. We've got the moon right here, and we have the distance, and the distance squared because we're going with this equation. Well, if you're typing this into the calculator, you're going to type in 6.67, and then you do that EE button, that second comma that gets you the E, that it shows E in the calculator, and then you just type in negative 11, and I hit equals to get in the calculator's memory, and then I hit multiplied, multiplication, whatever, the multiplication symbol, and then I hit 6.0, and I do that second, I get to the EE, second comma, which becomes the EE, and I just type in 24. I don't type in the 10. The EE does it for me. And then I hit equals, and it gives me a new number. So at this point in time, the calculator is showing me in its memory these two multiplied by each other. And I'm just going to hit, hit times. Once I hit times, I see what this is, 7.35. I hit the EE button, 22. I hit equals. I get this in the calculator's memory. I hit divide then, and so when I hit divide, I'm now on the bottom, and I'm going to have an extra parentheses. I'm going to put 1 parentheses, 2 parentheses, and I do 3.844, and I find the EE button. After that second comma, which is the EE, I hit just 8. I close parentheses. I hit the second squared button, or actually not second squared, just this button, the squared button. I get this right here. I close the parentheses, I hit equals, and if you do that right, the magic happens and you get 1.99 times 10 to the 20th newtons. So the key is not how you type in the calculator, but how you're getting the right answer every single time. So if you didn't get that right and you're doing this at home, make sure you try that again. Maybe try it a few different ways, maybe in parts, maybe do every single part separate, or whatever is going to help you get to that answer. But you should have an answer somehow that would round to a number like this. When I say round to it, you should have times 10 to the 20th. That's gonna be important. If you have 1.99 times 10 to the 15th, that's like a lot different. You want to have times 10 to the 20th. If this is like 2.1 times 10 to the 20th, or 1.8 times 10 to the 20th, still it's not that far off relative. But this is going to be an important number that you would see. Okay, what's the force of gravity between the Earth and Mars when they are a minimum distance of 5.46 times 10 to the 10th meters? So you have your values to plug in. Once again, just go ahead and try it out. I already talked you through the last one, but you should have an answer of 8.54 times 10 to the 16th, and the unit's going to be newtons because it's force of gravity. Okay, so this question is asking about the force of gravity between Earth and Mars when they're a maximum distance, that 4.01 times 10 to the 11th meters. So you're going to have the G from before. You're going to have the 5.972 times 10 to the 24th. So I just didn't round as much on this problem for Earth. for the mass. Then Mars is going to be 6.39 times 10 to the 23rd right there. And then we have our distance. Once again, make sure as you write this out, you should have all this written out, because you want to make sure that you did not forget that squared. That's where people make mistakes on this one. So I'm going to tell you how I'm going to type it in. I'll type in 6.67 e negative 11. So once again on the calculator, 6.67. Then I go and hit second, that comma button, which was going to give me the e. And then I'm going to go directly to negative 11. Students that are making mistakes yesterday were hitting the power. You don't have to hit the power. Don't hit that button. You just type in negative 11 at that point in time. This is a TI-84. There's calculator X and calculator 84. You can download online where you type numbers in the same way. And then what I'm going to do, actually, you don't need to. I did tell you slightly different the other day if you were listening to my lesson. But you can just do parentheses. Let the calculator do all this for you. It might make it easier for you than doing some of the steps on a problem like this. And so you do 5.972 E24. Once again, 5.972. Then the second E button. And then I would go directly to the 24. So this would have just had 24 down here, not to the power of. And that would be that part, close parentheses, open parentheses, 6.39 E23, so the same way as before. And then I would hit divide. So next I'd hit divide, and that would get to the bottom part, open parentheses, 4.01 E11, close parentheses. Then over here you'll see the square button. So hit that button, you're going to see a square, close the parentheses one more time, hit equals, and you should see this answer right here. So double check your work, make sure that's what you got, 1.58 times 10 to the 15th. And if you didn't get that, you could have possibly missed this, or just some sort of long numbers. You could easily miss some part of that long number somewhere. Number 11, what's the distance between Earth? Okay, so it's asking you for distance. It's giving you kilograms mass. It's giving you mass. It's giving you the force of gravity. So we have to rearrange this equation, which we did earlier, into this equation, and we plug in our values. Make sure you plug in all your values so you're looking at it. One thing I want you to notice here is this before on the bottom was d squared. This is just FG. It's not anything squared. This is just the force of gravity. So things switched around when we rearranged the equation. We already got rid of the squared because the squared was over here when we took the square root of this. So this is the way I would type this into the calculator. So second, that you want to pull in the square root button. Then open parentheses. That's this parentheses. Open again, that's that parentheses. 6.67 E negative 11. Close parentheses, open parentheses. 5.972 E 24. Close parentheses, open parentheses. 6.39 E 23. Close parentheses. And then what we want to do is we want to divide. So everything's still multiplied. There's still one extra parentheses to include everything we include right here underneath the square root. And we're going to go divided by open parentheses 5.1 times, E 15. Close parentheses, close parentheses. We finally closed that parentheses. We just kept everything underneath the square root. It equals, and you should see this answer right here. If not, you might want to do it in parts, do it a different way. So put 2.23 times 10 to the 11th would be your answer. Moving on up, we're going to go to number 12, and here we're asked for the mass of the planet. We're given force, we're given distance, meters, we're given kilograms, and so we're looking for a mass. Doesn't matter if you have mass 1 or mass 2. We're solving for one of these masses. Since we're given the mass of the Earth, the way I set it up, mass 2 would be the one we know. So we plug in our values just like that. And this is the way I would type this one in. 1.94 E17. Sorry, open parentheses, start over. Open parentheses 1.94 E17, close parentheses, open parentheses, 1.0 E11, close parentheses, find that squared button, square it, close parentheses, hit the divide, open parentheses twice. This is very important. You want two parentheses down here, open parentheses twice, 6.67 E negative 11, close the first parentheses. You're still in the denominator. You have that second parentheses there. Open it. 5.972 E24. Close it. Close it. You just closed off that second parentheses. It's going to keep everything together before it divides. You hit equals. When you hit equals, you should see 4.87 times 10 to the 24th kilograms. So just to go through, and I'm just going to zip through the answers. Once again, I'm not going to explain how to type the numbers into the calculator as much anymore. This is just a place for you to check, but make sure you check after you've done the work on the problem set. So then you'll revisit this right here. The universal gravity is 6.67 times 10 to the negative 11th. It's a really small number. And that tells you that strength is very weak. In fact, it's the weakest fundamental force in nature. How many times different is the force of gravity if the distance between objects is tripled? You do the law of 1 just like in our lesson before. 1's everywhere on the bottom. Only a 3, the distance is tripled, so you get 1/9. Once again, if you're making a mistake there, you forgot the squared. That's still something that has to be placed there, even when you're doing law of 1's. This problem, you double the mass in half the distance. So 1's down the bottom, you put a half in for D, and you put a 2 in for one of the masses, because it says only one mass. Make sure you still have that squared there, and you're going to get 8 times. If you're having trouble with typing this in, maybe try 0.5 squared. This one, initial force was 50 newtons, so this is a step further. It's still law of 1's. We still would go ahead and say, okay, the distance doubled. How much does it change? We find out how much it changes, and then we just take that and we multiply it by the original value. 1/4 times 50 is 12.5, and now we know newtons. We know exactly how many newtons, not just how many times it was. And then back to the longer equations. Once again, do the work. Make sure you're typing the numbers in correctly. If you made a mistake here, you might have forgot that square. That's most likely the place. Make sure you're using a G of 6.67 times 10 to the negative 11th, not 1, because it's not a law of 1's problem. It is going to be what it is, and you get 937.97 newtons. Next problem. When you plug it in, you should get 1.39 times 10 to the negative 5th newtons. Same place where students would make a mistake, right there, or maybe not, leaving this out or leaving a 1 there instead. Next question right here. Places where students make mistakes, they forget the square root. If you're not getting this answer, 5.4 times 10 to the 10th, you may have forgot the square root, and then besides that, just compare your work. Make sure you have this on your paper written like this before you type it into the calculator, because then you can see what you're possibly missing. Number 9, when you type that in, another one where you don't forget the square root. Make sure everything's underneath the square root, and you should have 12.8 meters as your answer here. Number 10, make sure you have double parentheses around the bottom, keeping everything down the bottom together. If you do that right, and you have all your numbers there, you should get 1.22 times 10 to the 74th kilograms.